Hello everyone. So this is a very short video just to look at the key features of the F block elements. First up, where is it? Usually the F block is appended to the bottom, a bit like an afterthought. Indeed, IUPAC, the International Union of Pure and Applied Chemists, the chemists' governing body, has just mandated that that's where it should be. However, conceptually there is a more useful place to put it, and it should fit like this, essentially in between the S block and the D block. This gives us what is known as the long form of the periodic table. It is very clear that everything is where it should be, but it's a bit of a nuisance to need such a long, thin bit of paper to draw it out, so you rarely see the periodic table in this format. The F block is 14 elements across, and we have 2 periods. Today, I'm adding in 2 elements, lanthanum and actinium, which arguably belong to the D block, but chemically there are good reasons to include them in the F block when discussing the chemistry of this collection of elements. So collectively, the first row are known as the lanthanides. After the preceding element, lanthanum, they include samarium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. The second row are collectively known as the actinides, after the preceding element, actinium. These include thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. It's more meaningful to consider each period at a time. So the first row of the F block, the lanthanide metals, are all metals, and they are all quite reactive, although less so than the S block, but more reactive than the D block elements. So while a freshly prepared lanthanide metal surface will tarnish in air in seconds, a much more vigorous reaction is observed with a smaller piece of metal. In fact, you can combine cerium and iron to get a brittle alloy called ferrocerium, which when you scratch it with the steel allows a dust of fine particles to break off. When these particles are small enough, the reaction shows a spontaneous combustion. Here's a good use of lanthanide as a fire starter. Now, metals tend to combine with elements on the right side of the periodic table, not including group 18, the noble gases. When we do this, the product is always a salt. The lanthanide ion is almost always a 3+ cation. You will see that occasionally there are some exceptions. So here are the known stoichiometric lanthanide fluorides. You see that the MF3 composition predominates, and that's because the M3+ ion is such a stable species. One of the unique features of this part of the periodic table is how remarkably similar is the chemistry of all of these elements. Chemically, the main difference between one lanthanide and the next is that the atoms and ions just get a little bit smaller as you progress across the period. Although the difference between neighbours is small, a change in size of about 1%, the cumulative nature of this change means that it's quite significant from one side to the other. This phenomena is known as the lanthanide contraction. Like the transition metal salts, salts of lanthanide elements tend to be coloured, although the colours are generally more pale than the similar salts of the D block elements. The other key feature about the coloured lanthanide salts is that the colour is characteristic of a particular lanthanide ion, and for the most part it is independent of the nature of the negative counterion. The use of lanthanides is rapidly growing. They tend to have very many specific sort of niche applications due to their optical and magnetic or electronic properties. Okay, now let's say something about the actinides. Firstly, like the lanthanides, they are all metals, being sandwiched between the metals of the S block and the D block. That fits with our expectation. The second key feature is that since these elements are at the bottom of the table, we notice that they are all unstable. They are all radioactive, and given enough time, they will all transmute into lighter elements. The radioactive nature of all of these elements has a huge influence on their abundance and their availability, and it can present a number of physical problems with their studies and usage. Not to mention the additional hazards to people and the environment of increased radiation dosage. Having said that, they are still a very important group of elements with unique chemical properties. The radioactive nature of these elements means that they all decay, ultimately into more stable elements. The rate of decay is far from uniform. We normally characterize the decay rate by a half-life. That is the time taken for half of the material to transmute into something else. So this is a rather ridiculous semi-log plot, which ranges 27 orders of magnitude. At the bottom is 10 to the power 0, that's 1 second in plain English. 10 to the power 2 is 100 seconds, that's about a minute. 10 to the power 6 is 1,000,000 seconds, and that's about a month. Look, bismuth, which until recently was thought to be indefinitely stable, actually decays, just very, 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 very slowly. The half-life of bismuth is 10 to the power 27. That's 100 million times longer than the current age of the universe. From this graph you can see that only thorium and uranium are stable enough to have lasted on Earth from the creation of the solar system to the present day. Everything else below this line can only exist on Earth in very small quantities and in a transient state before it turns into something else. The elements beyond uranium are known as the transuranium elements, and they are all man-made, synthetic. Neptunium, plutonium, americium and curium all have, by human standards, very long half-lives, making them much easier to study and use. But there's a bit of a drop down to berkelium and californium. These elements become more difficult to work with, and beyond that, the elements become extremely difficult to study, so our knowledge and understanding of the chemical behaviour becomes quite limited beyond this point. From a chemical perspective, we can look at some of their compounds, and the actinide fluorides are quite useful to illustrate a number of properties and trends. The first thing, for some actinides only a single fluoride compound is known, while for others there are many distinct stoichiometrically different compounds. Look at uranium and neptunium. They can form fluorides with anywhere between 3 and 6 fluorine atoms. But some stoichiometries are much more stable than others. I've highlighted the more stable compounds here. And what we see for the actinides is two distinct regimes of behaviour. Early on, it is the highest possible stoichiometry that is most stable. This is just like what we observe for the behaviour of the first few groups of the transition metal elements in the D block. But as we progress along the actinide series, the MF3 stoichiometry becomes more and more important. And so here, the later actinides behave much more like the elements in the row above, the lanthanides. I don't want to say much more at this stage. Generally, actinides tend to form positively charged cations, their salts tend to be coloured, and like all elements, their chemistry is unique. While applications of these elements are certainly focused on the nuclear industries, they are certainly not limited to nuclear fuels and nuclear weapons. For example, there is a red-hot plutonium battery powering the Curiosity rover as it explores the surface of Mars today. Every smoke detector in every house contains americium as a radiation source, as a stream of electrical current that in my house is blocked by the whiff of burnt toast. And historically there were many more daily objects that would have contained actinides, like uranium glass, which was very fashionable before World War II. Okay, that's about enough of a summary of the F-block elements, and if you survive until year 4, you'll get 8 more lectures from me on this subject, hopefully face to face. So in this unit, we have had a bit of a deeper look at some of the characteristic chemistry of all of the elements block by block. We can see that the periodic table very nicely orders the very many properties of these elements. But to make sense of why this is so, we need to look deeper into the world of atoms. We need to look inside atoms. And that's just what we will do in the next video. See you next time.